This PowerPoint video will be covering wave interactions. When waves meet matter, the interactions that occur depend on the matter itself. Now, very quickly, we're going to be talking about absorption, diffraction, interference, even though interference is kind of an exception because interference can occur even in a vacuum, so it does not need matter in order to interact. Reflection, refraction, and finally transmission. So let's get started. Absorption occurs when a wave meets matter and the energy is absorbed or taken in by the matter. So if we look here in this picture, we see this wave, and this is actually a ray, is hitting some matter here, and we see it's getting absorbed by that matter. So we see none is going through. It is being completely absorbed. All of the energy is being absorbed by this substance right here. How much energy is absorbed is dependent on the makeup of the medium through which that wave is traveling through. Next, we're going to talk about diffraction, which is the bending of waves around the edge of an obstacle or through an opening. The amount of diffraction does depend on the wavelength of the wave and the size of the obstacle or opening. So let's take a look at these pictures here. It says as the size of the barrier increases in length compared to the wavelength, the amount of diffraction or bending will what? Well, let's take a look. Here we have a small length and we can see a little bit of bending. Here we see a large length and we see quite a bit of bending. So we're going to say it is going to increase. So as the size of the barrier increases in length, the amount of diffraction will also increase. Let's see what happens in this scenario. This time, though, instead of the length that we're changing the width. So here we have a very, very small width. Here we have a very, very large width. So we can see as the size of the barrier increases in width compared to the wavelength, the amount of diffraction actually decreases. Now let's look at an opening. So if we look at these two pictures, we have two different openings. Here we have a very, very small opening. Here is a very large, well, not a very large, but a larger opening. And so we can see there is a lot more diffraction through the smaller opening. So as the size of an opening increases compared to the wavelength, the amount of diffraction is going to decrease. Okay, so that is diffraction. Now let's move on to interference. So interference doesn't really have to do with the medium through which a wave is traveling. It just occurs when two or more waves arrive at the same place at the same time and combine. We have constructive interference, which produces a greater amplitude than either wave. And then we have destructive interference, where the waves combine to produce a smaller amplitude. So here's an oscilloscope showing two waves combining. Now, an oscilloscope is just a device that converts sound waves into transverse waves so they can easily be measured. So here we have wave 1 that's traveling and wave 2, and we can see a crest is meeting with a crest, so therefore we have a combined amplitude of these two things. Over here, we have a crest meeting a trough. So this time they're going to have a smaller amplitude. As a matter of fact, in this case, there is no amplitude because they have canceled each other completely out. Here's another example of interference. Larger amplitude, smaller. Larger, smaller. Larger, smaller. So we can see constructive and destructive interference is occurring in this animation. Now let's talk about transmission. This occurs when a wave meets matter and its energy travels through the matter. Again, how much energy is transmitted depends on the makeup of the medium itself. So here we see, here is our incoming wave. It hits this matter. It goes through the matter and then it passes through to the other side and comes out. Okay, that is transmission, the passing through of that energy through matter. All right, next we have reflection, which is the bouncing back of a wave at the boundary of a different medium. We have incident waves, which are created by the energy source. So in this diagram, here is our incident wave. And then we also have the reflected wave. And so this is the wave that actually bounces back from the medium. When a wave encounters a different medium, some energy can be reflected, some can be absorbed, and some can be transmitted. It just depends on the makeup of that medium. As the similarity of the medium increases, the amount of energy transmitted also increases. So let's take a look at this animation very quickly. All right, so here we see very similar media. So we see the energy is transmitted. But now, let's change the thickness. Okay, so here we see the medium that it's about to hit is much denser. So let's see what happens now when they come in contact. Okay, so the majority of that energy is reflected, and we see just a little bit is entering into the new medium. So we don't know if that energy is going to be transmitted or if it's actually going to be absorbed by that matter. And now let's go ahead and change it out there. So now we have a very dense medium, or wave traveling through a very dense medium entering one that's not as dense. Let's see what happens. Okay, so we still see reflection, okay, and it was absorbed by this other piece of matter. So the closer they are in relation to one another, the more likely it will be transmitted through. All right, and the last interaction we're going to talk about is refraction. Refraction is the bending of waves as they pass to a new medium at an angle. What's important here is that refraction only occurs when the waves are traveling into a new medium at an angle. If they're coming head on, they're not going to bend at all because they're all going to slow down at the same time. So here we see an animation. This is where the wave fronts are coming and they are hitting, and you can see one part of the wave front is hitting before the rest of the wave. That is why it bends when it enters the new media. Okay, so the new medium now is making it bend because the wave fronts are hitting at an angle. Here, if they hit all at one time, they're all going to slow at the same rate, so there will be no bending. Okay, so these are the wave interactions that we are going to be responsible for knowing. This unit, this is the end, and it concludes our video on wave interactions.